Hey there, chemistry team. We're on to a new journey today. It stems off of last chapter. We looked at simple chemical reactions and how we write those as chemical equations and look at stoichiometry amongst all the species in that equation. But we're going to complicate it a little bit because the majority of what we deal with in general chemistry labs are solutions. We talked about that's why we did solutions in the last section. So we need to know if we're going to do chemical reactions that occur in solution, dissolved, and we're going to be focusing on aqueous solution. If we're going to write equations for that, it's not quite as simple if it's a pure gas or a pure solid or a pure liquid. All right? We need to truly understand how something exists when it is placed in water, whether it dissolves in water, reacts with water, etc., etc. What's going on. And our focus for this particular chapter is to predict the products, look at different types of reactions that occur in solution, be able to predict what products form. And there's some exceptions to that. And then how do we write those as equations on paper? Now we're going to find out there's several different ways of doing that because some things change when you put them in water. Gets a little complicated. So this particular topic, I'm going to start with this before we get into equation writing, because we need to know how something really exists. We need to look at it from an atomic or molecular level. If something is placed in water, what does it look like? Does it consist of ions or molecules, a mixture of both? What's going on? And how do we determine that? We want to get really, really good at this because I find it is a huge topic that students struggle with. If we can't see how something exists in water, we're going to really, 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 really struggle writing equations for reactions that occur in solution. All right? How can you write the equation if you don't know the formula for how something exists? All right. So we're going to call this predominant species in solution, or dominant, or major. When something is placed in water, how does it exist? So we're going to look at, or how does it truly exist? And really, there's only three ways based on this concept that you've probably heard of, electrolytes. You drink your Gatorade, get your electrolytes. What does that even mean? Well, to a chemist, an electrolyte is just something that when placed in water, whether it dissolves physically or reacts chemically, it forms ions, charged species. So when you're chugging down your Gatorade, you're getting your sodium ions, your chloride ions, magnesium ions, those kinds of things. That's all it really means. We're going to look at it as chemists as how something exists in solution. All right. So we're going to look at strong electrolytes, weak electrolytes, and non-electrolytes. When we're doing equation writing for reactions that occur in solution, the very first thought process when we're looking at a substance is to go, is that a strong electrolyte? If not, is that a weak electrolyte? If not, is that a non-electrolyte? Once you know what category it's in, we'll know how it exists in solution, right? So strong electrolytes, since an electrolyte is something that forms ions in water, we're going to define a strong electrolyte as something that interacts with water to 100, there goes a kitty cat, 100% extent and exists completely as ions, no molecules, right? Completely as ions. Don't step on the tablet, kitty! Oh, it's so fun recording with pets. Here he comes again! No, I'm gonna pause. For some reason, one of my cats just decided to walk back and forth and back and forth and back and forth. You gotta love cats, right? They lay right on your keyboards, right on your homework. You gotta love them. All right. So if we identify something as a strong electrolyte, which we'll do later, all right? I'll go through all the different kinds of strong electrolytes. We'll go, oh, that exists as ions only. All right, there we go. As long as you know how to find them. The next category will be weak electrolytes. So yeah, they form some ions, but not a whole lot. We have some experiments in introductory chemistry where we dissolve some species in water and put some probes and some electrodes in there, some probes to see if it lights a light bulb or makes an LED blink or glow or something like that. Because ions are charged species, right? So if they're able to freely move in water, they can complete a circuit and light a light bulb. We don't really do light bulbs anymore because I kept zapping myself. So we just have a little battery with these LEDs that go. Kind of fun. So a strong electrolyte, lots of ions, that would make a light bulb glow really, really bright. Weak electrolytes, it would glow, but dimly. Non-electrolytes, of course, if there's no ions, it wouldn't glow at all. So weak electrolyte produces some ions, but is mostly retained as molecules. So they're the hardest ones because they're a combination of molecules and ions, but dominantly molecules. All right, and in second semester general chemistry, we'll be able to calculate what percentage are molecules and what percentage are ions. We'll be able to do that, but not at this particular level. All we need to know is that the huge majority, probably over 95% of the particles for a weak electrolyte in water are going to be molecules, neutral molecules, and then probably 5% or less, give or take, will be ions. So when we're writing equations, how do you write it? If it exists as two separate forms, what do you do? Well, you do the dominant one. That's why it's called the predominant species in solution. So strong electrolytes you would write as ions. Weak electrolytes we will write as molecules because that's the dominant form. That's what we're going to do. All right, non-electrolytes, of course, they're not going to form ions in water. So if they dissolve, they don't break apart into cations and anions, things like covalent molecules, etc., sugars. We'll look at that later. And so no matter what they do and no matter how they interact with water, they will not form ions. So they are 100% as neutral molecules. Let's look at the three different types of equations we're going to get into to show you how we represent species. And then we'll go through each of these in turn, and I'll go through the different types of species so you can recognize, oh, that goes into this category, that goes into that category, etc., etc. All right, let's start with strong electrolytes. We're going to look at there's really two, but we'll break it up into three categories. And again, these are things that are 100% as ions in water. So first are going to be our soluble ionic solids or salts or compounds, however you want to call it. And so you're going to need your solubility chart for that one, which tells you which ionic compounds dissolve in water and which ones do not. So we're going to simplify it and make it very black or white. Next semester, we're going to have things that are slightly soluble, etc. But we're going to say either they dissolve to 100% or they don't dissolve at all. We'll keep it that simple in first semester general chemistry. So we'll have to look at the solubility chart in a second here. So I'll go grab that. So these undergo dissociation. It's a physical. The water just pulls the cations and anions apart. That's all that's happening. And this would be a dissociation equation. So say we have sodium chloride. Right? This undergoes 100% dissociation, so it does not exist as NaCl molecules. It exists 100% as sodium ions and chloride ions. That's it. All right? Notice the 1-to-1 ratio. Over here, if we take lead-2 nitrate, this breaks apart, dissociates to 100% extent. You have a subscript of 1, right? So you get 1 mole of this produces 1 mole of the lead-2 ions. See the subscript of 2 on the nitrate ions? That subscript becomes the coefficient over here. So you get 2 moles of nitrate ions. So 1 mole of lead-2 nitrate exists in solution as 1 mole of lead-2 cations and 2 moles of nitrate anions separately moving around in water as individual particles. And those are the predominant forms in solution. We're going to have an equation that writes them that way. We're going to have one equation that writes it this way, and we're going to have another equation that writes it as it truly exists. So what I want you to do is go find your solubility chart real quick, and we will walk through that. All right, did you fetch your solubility chart or solubility rules? Should look something like this. Now, depending on the class you take, these will all look different. All right. So now we're not going to focus on the bottom for it. We're going to only focus on the top, and these are soluble compounds. All right. So what you do is you take a look at the box over here, and it gives you different types of ions. And if you see any of those ions, those are always going to dissolve in water to 100% extent. Those are considered strong electrolytes. They will, again, exist as cations and anions separate from each other. So you get the alkali metals. And just to be general, I do at this level all the alkali metals, ammonium ions. And there's no exceptions to that. If you ever see those are always going to be separated cations and anions. Most of the halides, right, are going to be soluble, very low charges, right? Think Coulomb's law. The lower the charge, the less attracted they are to each other. The higher charge, the more attracted. So higher charged cations and anions tend to like to stay as solids. The lower charged ones, we'll find out the bigger they are and the lower the charge, the more likely they're going to dissolve 100%. So these are exceptions. So that the chlorides, bromides, iodides, they tend to separate out as strong electrolytes unless they're combined with one of these. Pretty simple. Fluorides, You know, it's really tiny, so it tends to form a few more, stay as a solid a little bit more. The nitrates, nitrites, most of these, the chlorates, the chlorites, the bromates, the bromites, they're really big and low charge. They tend to separate out as strong electrolytes. Sulfate, even though it's a -2, it's pretty big. It does form a few precipitates here, stays as a solid, but most sulfates are going to separate out. So just take a look at the top part. These are the insoluble ones that tend to stay as solids. So these are the ones, if you see any of those, boom. Or if it says in the problem, it is a solution. Right? If it says it's a solution, regardless of what that table says, you're going to separate that out as a strong electrolyte. Right? So those are your most common strong electrolytes. Let me do the next two. Next category out of the 3 strong electrolytes will be strong bases. And we looked at these when we looked at equivalents. Remember the OH minus, right? Extracts an H plus, so that's functioning as a base with 1 equivalent per mole. So anytime you see the OH minus, in most situations, we're going to treat it as a strong base, especially the alkali metal hydroxides. In my class, all alkali metal, group 1A, sodium hydroxide, potassium hydroxide, rubidium hydroxide, all of those, we're going to treat those as strong bases. They're essentially just ionic compounds. They dissociate just like soluble ionic compounds, so we'll treat them as such. So sodium hydroxide, 1-to-1 ratio, that will to 100% extent give you the sodium cation and the hydroxide anion, exactly like you would for sodium chloride, right? And these would be the predominant species in solution. That's how it would truly exist. There's some debate on the alkali metal hydroxides, the group 2A ones. The majority are considered insoluble, and yeah, that is true. But add enough water, you can dissolve, things to a much greater extent. We'll look at solubility in second semester general chemistry. So in my class, we're just going to simplify life and call the alkaline earth metal or group 2A hydroxides also strong bases. So the calcium hydroxides, the magnesium hydroxides. Yeah, there's some debate about that, but we're just going to generalize it. And so if I say you have a solution of magnesium hydroxide, it says solution, we're going to treat it as 100% soluble to give us the magnesium ion. And notice the subscript of 2. So you might get a different professor that says only a couple of the group 2A metal hydroxides are soluble, the rest aren't. That's okay. Go with whoever you got. We're just going to generalize it and say the group 1A and 2A metal hydroxides are going to be our strong bases. Treat them just like ionic compounds. Easy peasy. Let's look at the third one, strong acids. Strong acids. Fortunately, the majority of the acids are not strong for us, but these cause some brain spasms for a lot of students. So a strong acid does not physically dissociate in water, although some kind of introductory professors may treat it like that just to simplify it, but it's not a soluble salt. It doesn't break apart into cations and anions. It reacts with water. It's a molecule. But when you put that molecule in water, it donates its H plus like acids do. Boop, water picks it up, forming H3O plus, which is called the hydronium ion. And then you're left with, I just cover up the hydrogen, A, which is, we just do this as any acid, some generic acid, so you get the A minus over there. Next semester we'll call that a conjugate base. So if this happens to 100% extent, this is the predominant species in solution. They don't exist as molecules. They exist as the hydronium ions and the anion from the acid that forms. Oh, so we're going to only look at 6 strong acids. There's more than 6. A lot of them are weird organic ones, but we're only going to look at 6 strong acids in this class. Let's list those out. And again, that may differ depending on who you're taking, but we're going to treat just 6 in this class. We're going to take hydrochloric acid, hydrobromic acid, and hydroiodic acid. They're all hydrohalic acids there, but not HF. Turns out that was a weak one. Nitric acid, sulfuric acid, which is a tricky one, and perchloric acid, HClO4. There's some debate with HClO3. That's right on the edge. So we're going to treat those 6. I would memorize those 6. So if you see an acid and you see one of those 6, boom, strong electrolyte exists as hydronium ion in the anion. If it's not one of those 6, weak acid, and we're going to treat it as the molecule. It'll be a mixture of both. All right. So let's do a couple examples for what are called, this is called an ionization reaction. Ionization equation. Because what we're doing is we're taking neutral species and forming ions in solution by a chemical reaction. So that's not a dissociation equation, it's an ionization equation. So let's do a couple on the board and then we'll get to weak species. Do it for me, gang! Let's take nitric acid and hydriodic acid, do the ionization equation for me, and that'll go to 100% extent. So pause it if you have to. Donate your H+. Boop. That comes across. Boop. That comes across. Write your products for me, and let's see what we get here. All right. Of course, the water picks up the H+, so you get hydronium every time. So let's put the hydronium ion for both. That's pretty easy, right? And then all I do still today after 30 years, I cover up the hydrogen and go, oh, it's I. And it loses a plus, so you get I-. So it releases that. And that happens to 100% extent. Same thing here, cover up the hydrogen, you're left with the nitrate ion. And again, those occur to 100% extent, so these are the predominant species. So when we do equation writing, there's some equations we're going to write them as molecules, and other equations we're going to write them as their predominant species. And these are strong acids, which are strong electrolytes, which will be as ions, just like that. All right, let's look at weak electrolytes now. All right, weak species, there's less. There was 3 kinds of strong species, strong electrolytes, right? Soluble ionic compounds, strong acids, and strong bases. For weak species, there's only 2. We're going to have weak acids and weak bases. Now, again, these exist as both molecules and ions, so it can be a little bit confusing. But let's take a look at the reactions. So weak acids, they're acids, just like strong or weak. Strong acids and weak acids both ionize in water exactly the same way. They donate their H+ to the water molecule, forming hydronium ion. The only difference between strong and weak is the strong ones do it to 100% extent. If I put in 100 molecules of HCl, a strong acid, all 100 will ionize in water. There'll be none left. It'll be 100 ions of H0+ and 100 ions of chloride, right? If I have a weak acid, it will react the same way, just to a tiny extent. The amount isn't important, just that you know it's small. So most of them are usually about 5% or less, give or take. The main point is it's very small, right? Even if it's under 50%, that means if I put, say it did it to a 5% extent. If I had 100 molecules of a weak acid, only 5 would react. Which means 100 minus 5 is 95. 95% of it would be as the original molecule, and only 5% would be as the hydronium ions and the anions of the acid. So it exists as both. Sometimes we represent that with a reversible arrow. That'll be more important next semester. But since the dominant species is the molecule, that's how we're going to write it in solution. So what's the weak acid? I'm not going to list up hundreds and hundreds of weak acids. It's any of them that aren't one of the 6. Right? The 6 strong ones. Memorize those 6 strong acids. And if it's not one of those, it must be weak. Hey! Works out good. So let's take a look. For example, let's take HBrO2. What's that? Bromous acid comes from the bromite ion. Right? That is not one of the 6. HCl, HBr, HI, HNO3, H2SO4, HClO4. It's not one of those 6, so it must be weak. So this is a weak acid. That will react with water. It's going to donate its H+, exactly like the strong acids do, but to a very small extent. So let's say that goes less than 5%. You know, I'm just saying 5%. So we're going to get hydronium ions. And then we'll get BrO2 or bromite ions. But it actually goes back and forth. So typically the indicator for a weak species will be the reversible arrow. So all of them exist. The neutral molecules exist. The cations and anions exist all together now at the same time. But dominate this. So these are the dominant species. So that is your predominant form in solution, the molecule. So in the next video, when we look at ionic equations, we do a special type of equation where we're going to represent species as they truly exist in water. If it's a weak species, we're going to write it as a molecule. There you go. And it's the same for all weak acids, any that aren't one of the six. I guess that's not too tough, right? As long as you memorize those six strong ones. Do it now. Let's look at weak bases. That's a little trickier. And we looked at them briefly when we did equivalence normality. Hopefully you went and reviewed our introduction with equivalence for weak bases. But these are going to be ammonia and ammonia derivatives, which are called amines, where you've got this nitrogen with a lone pair. I'm not going to draw the lone pair this time. And ammonia has 3 hydrogens in a lone pair. We can replace a hydrogen with a carbon-based group. That's where it gets organic. Oh, sorry for swearing. And in this case, I have replaced 2 of the hydrogens with these CH3 or methyl groups. I can put a big chunky carbon group here. It doesn't matter what these carbon groups are. It's irrelevant. What matters is you've got a nitrogen atom with a lone pair on it. And what that means is it can accept or take an H+. And that's what bases do. Acids are proton or H+ donors. Bases are proton or H+ takers or acceptors. So in this case, they're taking an H+ from water. So what are we going to get if water loses a hydrogen and a positive charge? So it loses a hydrogen, so you get 1 oxygen, 1 hydrogen, and you lose a positive charge, so it goes from neutral to a -1. So you get OH-. That's why it's a base, my friends. You're forming OH- in solution, says Svante Arrhenius. And we'll see if Bronsted-Lowry defined it as a proton taker or acceptor. Svante Arrhenius defined it as something that produces OH-. Now, since that's weak, it's going to do it as in a less than 5% dish form. So the dominant species would be the molecule. Now, what else do we form? Well, that picks up a hydrogen, so that'd be NH4, and it went from neutral, picked up an H+, so it becomes positive. So you get NH4 plus the ammonium ion. For this one, we pick up the hydrogen, so we're going to stick another hydrogen on the nitrogen, and it goes from neutral to being a +1 charge. Right? So it's the ammonium form of that. So let's redraw this. Gets a little crazy. And let's stick that hydrogen on there. And again, you don't have to circle the positive charge. A lot of organic chemists like to circle the positive charge. Not important. Or you could write it as NH2. So you could do this and just go NH2 plus. Either way, doesn't matter. You're just showing that hydrogen connected to the nitrogen atom. And there you go. And since these are weak, 90+% of it will exist as the molecule. 10% or less typically will exist as the ion. So if we're writing this as it truly exists, these are the predominant species in solution. So weak bases and weak acids we will write as molecules in solution as their true form. One left. We saved the easiest one for last. Non-electrolytes. They don't react with water to form ions, so they're really easy. They just exist as the molecules like you originally wrote them. Yay for us. This one's my favorite. You don't have to think too much. All right, non-electrolytes. right? Whether they interact with water or not, they are not going to form ions, all right? So they don't form ions in solution, which means they only exist as molecules. That's how we're going to write them in our ionic equations later on down the road. So that would be insoluble ionic compounds. Looking back at your solubility chart, they would be the ones on the bottom. See the super high charges, right? There's exceptions, right? Of course, with the alkali metals and all those kinds of things. But pretty much the cations and anions with really high charges or are really small, like hydroxides, we're going to treat those as insoluble. So we'll put a solid next to them and write them as, they're not molecules, really, they're ionic compounds, but we're going to treat them like molecules when we write them in equations in solution. Pretty much anything with a solid after it, we're going to treat it that way. On top of insoluble ionic compounds, we're going to treat soluble covalent species. Right? If it's insoluble, you just leave it as a solid, right? It's not that big a deal. But lots of covalent sugars and things like that, sucrose, glucose, it does not consist of anions and cations, and it doesn't ionize or react with water. So usually we put the water over the arrow to represent a physical process, and that dissolves, and we all know sugar dissolves quite readily. So, but it retains its original molecular form. You just change it from a solid to AQ. So that's how we would represent it in solution, right, as the molecule. Other covalent species, you'll probably see like nitrogen. Say we take some nitrogen gas, dissolve that in water. Well, it's not very soluble, but some of it might. And if you get it in solution, it'd be AQ, or oxygen, right? Now, there's other covalent molecules like carbon dioxide that actually react with water. That's a different scenario. So we're looking at non-reactive covalent molecules that we can get dissolved to some extent in water. You just write them in the original molecular form with an AQ. Right, so I'm just going to briefly summarize it all up on here, but you need to practice this. Here's a quick little snapshot summary of what we did. So here's your 3 strong electrolytes, which exist as ions in solution, 100%. Our 2 weak electrolytes, which exist as both molecules and ions in solution, but predominantly molecules. And our non-electrolytes, which exist only as molecules, 100%, which are your insoluble ionic compounds and your soluble covalent species. And I added non-reactive. So some things react, that's not going to count. All right. Pretty much essentially, you're just going to look at things that are in solution. Anything that's solid, liquid, or gas, we're going to write that as a molecule. But if it's aqueous, we have to look at it and go, oh, aqueous means it's dissolved in water. So we have to look at it and go, if it's aqueous, is it strong, weak, or non-electrolytes? And if it's strong, split it into ions. If it's weak, we don't. Predominant species in solution. So we got to understand electrolytes to do that. And this is you're going to greatly appreciate if you understand this when we do equation writing for reactions in solution. Whew, sweating on that one, my friends.